Okay, gang, in this next section, what we're going to do is we're going to calculate volumes or revolution again, but this time we're going to use a different method. This is called the shell method. All right, now before I get into that, let me just remind you a couple of things from the previous lecture, okay? Notice in this figure here, I've got a circular cylinder, and we remember that its volume is equal to pi r squared times h. And we had mentioned that the pi r squared was actually the area of the circular top and the circular bottom. In other words, we say area of the base times the height will give you the volume of the solid. Now, when we were using the disk method, it was a very thin circular cylinder. That's this figure to the right, this one right here. Okay. And notice in this case, because it's so thin, instead of referring to the height as, well, the height, we call it instead the thickness. But the volume of it is still the same. Okay, so it's the area of the base, pi r squared, times the thickness. Still the height, but when it's such a thin disk like this, we usually refer to the height as the thickness. Okay, now the next thing I want to do is consider the cylinder on the left-hand side. Gang, let's suppose that you take this cylinder to be hollow. Okay, so it has no volume now. Okay, think of like a soda can where you cut the top and the bottom off of it. Okay, you know how thin that is if you unravel it, right? It's going to actually look like a piece of paper, okay, or a piece of tin. Is actually what it's going to be. All right, so I took the liberty of drawing that right here. Okay, so this is the circular cylinder above. Okay, so right here, right where I took our circular cylinder, imagine slicing it down from top to bottom in a vertical fashion and unraveling it, okay? And we're going to get this rectangular shape right here. Now, because it was circular to begin with, the length of it, right, the length of this is actually going to be 2 pi times the radius, right? That would be the circumference of it, okay? That's the circumference of the cylinder, 2 pi r. But when you unravel it, it becomes the length of the rectangle, okay? The height, of course, is this right here. Now, the area of it would be the length times the width, okay? So 2 pi r times h. So it's a plane, kids, it's a plane region, okay? It's a plane region. So it has no thickness to it, and so therefore it has no volume. Let's do this though, right? Let's give it a little bit of a thickness, okay? A little bit, say maybe a differential thickness, okay? Okay, so it's a thickness, and I'll mention that here. And once you give it a thickness, gang, now it's got volume. It's like it's a three-dimensional rectangular slab, for lack of better words, right? So now the volume of it would be this. Okay, you know what it's going to be? It's going to be the area times the thickness. Okay, the area times the thickness. Well, the area is above. We said that's going to be 2 pi r times h, and in parentheses, I'll just put the thickness. Okay, and that'll give you the volume of that cylindrical shell, we call it. Okay, cylindrical shell. All right, so let me go over here. Okay, so let's imagine this is our cylindrical container, so to speak. It's empty, it's hollow. Okay, it's the same shape that we were looking at a moment ago. And what I did, gang, is I rolled it back up again. Okay, here's the thickness to it. Okay, notice I gave a little bit of thickness to it. So this shape right here is the result of taking that rectangular slab and rolling it back up again. We call that a cylindrical shell. So remember when we referred to that as like a soda can? A soda can with the top and the bottom removed, that's like a cylindrical shell. It does have a thickness to it. I mean, is barely detectable, but it's got a thickness to it, okay? So we refer to this as a cylindrical shell whose volume is equal to the following, and I'm going to spell it out in words, okay? 2 pi times the radius times the height times its thickness, okay? That's the volume of this very, very thin shell, okay? Now, again, listen, it's so thin, we refer to it as a differential volume. Remember, we used that terminology in the lecture about volumes by using the disk method, okay? So how is this going to be helpful for us? Well, consider the following. Let's suppose that we take the basic square root function from 0 to 4, okay? And we'll bound it on the right-hand side by the vertical line x equals 4. And so we're referring to this region right here, okay? Let's also suppose that I want to take this region and revolve it around the vertical line x equals 4. That's going to be our axis of revolution. Okay. Now, you know, we start with a differential rectangle. Okay, so being consistent with what we've been doing for a while now, it seems. Here's our differential rectangle. Okay. All right, now we're going to revolve the whole region around this vertical line. What would the red rectangle look like? Take that differential rectangle, gang, and sweep it around the axis. Here's what it sweeps out. Okay, it sweeps out one of those very, very thin cylindrical shells. Okay, now that's just one. Let's draw a couple more. Let's use different colors, okay, so we can see it a little bit better. Okay, here's a cylindrical shell right here. So for that one rectangle, here's the shell that it sweeps out. Okay, here's another cylindrical shell. So rectangle here. So what we imagine happening here, gang, is that the entire solid, right? So when you take that region and you revolve it around the vertical line, okay, let me continue that on. It would look something like this, right? Okay, so it would look like this bump, so to speak. And we want to calculate the volume of this bump. And what I'm doing is I'm filling it up with a whole bunch of these cylindrical shells. They look like Tupperware bowls, don't they? But anyway, so that's the idea. Shells inside of shells inside of shells, and so on and so on and so on, okay? Eventually, there's going to be so many shells inside of this that they're going to blend into each other, gang, and it's going to look like one smooth solid, okay? So instead of using discs, we're using cylindrical shells. Now, make a note of this because this is important. In order to use the shell method, your differential rectangle must be parallel to the axis of revolution. That's an important distinction because remember we said previously to use the disk method, the differential rectangle had to be perpendicular to the axis of revolution. Okay, so the disk method, your differential rectangle perpendicular to the axis. For the shell method, your differential rectangle has to be parallel to the axis of revolution. Okay? All right, let's try some examples. Might as well go ahead and do this, right? We were using the figure above, but it got messy. All right, so I'm going to take the basic square root function. I'm going to bound it on the right-hand side by the vertical line x equals 4 and below by the x-axis. We are going to take this region and we're going to rotate it around the vertical line x equals 4. All right, so here's the axis. Let me use a different color. The axis, we'll make it green, okay? Okay. All right, as always, we're going to introduce our differential rectangle. So somewhere between 0 and 4, choose a generic x, they may be here, draw your rectangle. Okay, label the rectangle. Okay, since the bottom of the rectangle is on the x-axis, gang, I'm just going to leave the figure the way that it is. Okay, now draw the shell. Okay, take that one rectangle, rotate it around the axis. Okay, all right, let's label the dimensions of it. The reason I say this, and I'll put the reminder right here, the volume of that one shell, okay, dV, right? The differential element of volume in this case is a shell, not a disk. 2 pi times the radius times the height times the thickness. Okay. All right, let's see. Here's the radius right here. Let me use a different color. This horizontal distance right here, that's your radius. Gang, what is that horizontal distance? Yeah, good. It's 4 minus x. The radius is 4 minus x. Good, good, good. What's the height? Well, here's the height. What is that vertical distance? That turns out to be the length of the rectangle that created the shell. What is that vertical distance or length? Yeah, it's the y coordinate, isn't it? It's square root of x. So here, I'm going to say h equals square root of x. Okay? And then finally, the thickness of it, well, that's going to be dx. Okay, remember the thickness of the width of the rectangle is going to become the thickness of this shell. Okay, and if the width was dx, then the thickness is going to be dx. All right, so let's put this all together then. Okay, and I'll take the liberty, gang, of distributing this square root of x through. And you'll notice I converted the radical symbol to fractional exponents in anticipation of using the fundamental theorem in the next step. Okay, so the total volume, right? The total volume is equal to the sum of all of those individual elements, in this case shells, as they all range from x equals 0 to x equals 4, and they're all given by this expression. Okay. After that, as usual, straightforward integration. Okay, you can read off the antiderivatives term by term and move the 2 pi through the integral symbol. Okay, I'll leave that to you to finish. Okay, in this example, I'm going to take a steep diagonal line like that. And I'm going to take this and I'm going to rotate it around the x-axis. Now the region is going to be bounded. Actually, you know, let's go back to that. Let's be consistent with the color, right? Let's make it this triangle right here. Okay. Now, when I take that triangle and rotate it around the x-axis, you know what it's going to do? It's going to sweep out a very thin cone. Okay. It's going to sweep out a cone. And I want to find the volume of this thing. Okay. Now, remember what we said. In order to use the shell method, the differential rectangle we use has to be parallel to the axis of revolution. So that means, gang, somewhere between 0 and 6 along the y-axis, I'm going to have to choose a y, say maybe right here. And the rectangle that corresponds to it is right there. Okay, now I need to label the ends of that rectangle, but I really need to figure out what the equation of that diagonal line is right there first. Okay, well, rise over run, and it goes right through the origin. Okay, all right, so let's label our rectangle. So on this side, right here, we're going to have 4y. On this side, okay, that end, the x-coordinate is given by 2/3 y. Okay, now the shell that it sweeps out looks like this. Okay, all right, so let's make our notes right here. So the volume of one shell, dV, okay, is equal to 2 pi times the radius times the height times the thickness. Now, gang, notice in this case, because the rectangle we use to make the shell is horizontal, right? It's horizontal. That means its thickness is going to be dy. Okay, so let's figure our dimensions like we did before, okay? All right, this will be our radius right here, yeah? Okay, that's the radius of the shell. What is that vertical distance? Yeah, good, it's y. Very good, gang, it's y, good. So the radius is equal to y. So let me put that over here. So 2 pi, the radius is y. The next thing is we have to figure out, well, what's the height? Well, it's a cylinder and it's laying on its side. All right, so that means that this dimension here, that's going to be your height. Okay, you kind of have to cock your head to the side. See that? So the height then really comes down to what is the length of that horizontal rectangle. you're going to be finding the difference of the x coordinates. In this case, 4 minus 2/3 y. Okay, and I'm going to distribute the y through. And that will represent the volume of just that one shell. The total volume, let's go down here, is equal to the sum of all those individual elements. And those elements will range from y equals 0 to y equals 6. Okay, y equals 0 to y equals 6. And all those elements are given by this expression. Okay, now straightforward integration after that. Okay, let's carry this one through. Notice, kids, that we have y, the variable y is in both terms. And so that means that this bottom limit, y equals, or right, yeah, y equals 0, will not contribute anything to the answer. So it really just comes to the 6. Okay, and then whatever that, whatever that is when you go to simplify it. Okay, so that's going to be your volume, and obviously go ahead and simplify it. Okay, but notice the difference, gang, between the disk method and the shell method. So is one necessarily better than the other? So that's going to depend on what the region looks like when you sketch the graph. Okay, a good figure, gang, I can't overestimate this. It's really necessary to have a good figure as best you can when you start out with these problems. And then depending on what the region looks like, you decide, should it be the shell method? Should it be the disk method? That's just going to depend. Okay, let's suppose that we have this region that's bounded by the 4 equations, y equals x squared plus 6, so the squaring function shifted up 6 units. And then we have the vertical line, x equals 6, and then the y-axis, and then the x-axis. And we're going to take this region and rotate it around the y-axis. Okay? Suppose that we decided we were going to try the disk method. That would require that our differential rectangle be perpendicular to the axis of revolution, in this case, the y-axis. So again, here's what that would look like, okay? Somewhere between the 0 and the 6, say maybe here, right? There would be your very thin rectangle, okay? But there's something else here. Notice that when you get to the 6, look at this. Okay, when you get beyond the 6, the rectangle would look like this. Okay, see what happened there? Okay, notice that the right-hand side of both rectangles touches the vertical line x equals 6. No problem there. But the left-hand side of each rectangle, well, here, the left-hand side of the rectangle, getting anywhere between 0 and 6 along the y-axis, the left end of the rectangle will always touch the y-axis. But once you get beyond the 6, the left end of the rectangle touches the curve x squared plus 6. Remember what we said when we discussed areas? If ever there is a change in the top or the bottom or the left or the right of the differential rectangle, then it's going to require a separate integral. Why do we care? Well, who wants to do more integration than you have to, right? Work smarter, not harder. In this scenario, we would need one integral to go between 0 and 6. That would take care of all this part. Then we would need a totally separate integral to take care of the top portion of it, which would be this wedge right here, okay, when it goes around the y-axis. So you need two separate integrals, okay? Now, you can save yourself a little bit of trouble. The bottom portion would sweep out a solid circular cylinder like that. And we know that the volume of that piece really is just pi r squared h. Okay, we don't need an integral for that. Okay, we're thinking on our toes now. But you do need an integral for the top part like we discussed before. All right, I think we can save ourselves some trouble though. Here's another alternative. Okay, take the differential rectangle, turn it sideways from where it was before. In other words, make it vertical. Say here. Now, when that rectangle goes around the y-axis, it's going to sweep out a shell. And notice that no matter where you place that rectangle, the top of it will always be on the curve x squared plus 6, and the bottom of it will always be on the x-axis. So if we decide instead to use the shell method, it's only going to require one integral, less work. Okay, so in this scenario, it pays to use the shell method. All right, so remember we said a few minutes ago, which method is better, the shell method or the disk method? Well, sometimes it just comes down to a matter of preference. Other times it's just a matter of simplicity. In this particular case, it's much simpler to use the shell method because it only requires one integral. So be on the lookout for that, gang, when you're working through your problems.